calculus was born out of what we would call the gradient problem. If we were to consider this graph that we have here, it depicts a straight line relationship between voltage and current. Perhaps this was a graph obtained from students who were trying to verify Ohm's law. Now, the thing about straight lines is that if we wanted to know how one quantity changed with the other, perhaps current changing with voltage, all we need to do is find the gradient of this straight line. And the simple thing about straight lines is that the gradient is equal everywhere. So for straight lines, gradient is equal everywhere. However, if you have a situation where two quantities are related in a way that it's not linear, for example, look at this relationship here. Bacterial growth is related to time. Now, this is not a linear relationship. And let's just say, when you look at this curve, you want to know how the number of bacteria changes with time. You'll realize that it's not the same everywhere because the gradient here is different from the gradient here. Here, the gradient is different from there. Here, the gradient is different from here, and so on. Therefore, the problem arises, how do we now find the gradient of a curve at a particular point? See, with a straight line, all you have to do is find one gradient and your problem is over. However, with nonlinear relationships, with curves, the curve changes gradient from point to point, right? If we were to say curves changes gradient from point to point. And that's a problem, because if we have to find the gradient at each of these points of the curve, it's going to be a tedious operation. Perhaps you recall when you were in high school and you have to find the gradient at a particular point on a curve. What you had to do? You had to draw a tangent at that point and then find the gradient of that tangent. And then the gradient of the tangent at that point is going to be the gradient of the curve at that point, as we see in this diagram here. So let's say we have a curve in red, and we want to find the gradient of this curve at x equal 2. So we want to find the gradient here when x is 2. So what do? We draw a tangent, you see in blue there, and we take two very nice points, and we calculate the gradient of that tangent. And the gradient of that tangent, or the gradient of the tangent at x equal 2 is equal to the gradient of the curve at x equal 2. However, you will realize that there is a problem with this, in that if we have to find the gradient at several points in this curve, you would know that we have to draw a tangent at all those points. And you know the problem that will come when we try to draw tangents at a point on a curve. Everybody's tangent might very well be different, right? You might not get it right. And therefore, it's a tedious process. And therefore, relationships that are nonlinear between quantities, especially in the sciences, became problematic to really investigate and to study, because to find the gradients or to find out how one quantity is changing with another at a particular point posed a major problem. And that's the problem that Sir Isaac Newton and Gottfried Leibniz, they tackled independently. Now, what is the idea they used in order to solve this problem? They used the idea of a limit. Now, what are we talking about here? Let's consider this graph. So this graph, this curve, that's this curve here. It's the curve y equal x squared. And let's say we want to find the gradient of that curve at this point here, x. Sorry, at the point P, when the x coordinate is x. So the coordinates of P are x, x squared. Now what Newton and Leibniz did was they considered, what about if we were to draw what we refer to as a secant from P to Q? So they choose a neighboring point to P and they connect P and Q with what we call a secant. So let's say that, well, okay, the coordinates of Q is x plus h and x plus h squared, right? Because the curve is really x squared. So the x coordinate is x plus h, the y coordinate is going to be x plus h squared. And they took the gradient now, they took the gradient of that secant PQ. Now, if we were to look over here, that's what the gradient is going to be, right? Now, if we were to simplify that using some algebra, what we're going to get is this. Simplifying further, we're going to get this. So the gradient of the secant PQ is equal to 2x plus h. Now, what Newton and Leibniz said, what about if we were to move Q closer to P? As you move Q closer to P, what's going to happen is h is going to get smaller. But as you move Q to P, what will happen? Eventually, PQ, let's say Q comes right up here. And we reduce Q up to here. PQ is essentially going to be almost like a tangent at P. So PQ, the secant, is going to almost approach a tangent at P. And when that happens, h is going to become very, very small. They call this idea the limit of the gradient of PQ. So they're saying that the gradient of P is equals to the limit of the gradient of the secant as h tends to 0. And if we were to look at this expression, if h tends to 0, or we can say it's practically 0, well then 2x plus h becomes 2x. Therefore, they said that this 2x now is what we will refer to as the gradient function of the function y equal x squared. And with this gradient function now, you can now calculate the gradient of y equal x squared at any point. You just have to have the x value and you substitute it in 2x and you get the gradient. But before we move away, I want you to grasp the idea that Newton and Leibniz came up with, in that as you move Q closer, if Q gets closer and closer and closer and close to P, the secant eventually, it's as though it has become a tangent at P. So what we say is that the limit of that secant is equal to tangent at P. And that's where the idea of the limit came in. It's when you shrink H so small that it's practically zero. To help you visualize that some more, look at this graph. So as you take Q and you bring it closer and closer and closer to P, the secant basically becomes a tangent at P, and H shrinks to almost zero. And therefore, we say the limit of the secant PQ is equal to the gradient of the tangent at P. And there is where, a lot of ideas in calculus, in differential calculus, in fact, was born out of. And they came up with these formal definitions. So the function f prime, or the derivative of f, defined by this formula here, f prime x, or the derivative of fx, is equals to the limit as h tends to 0 of fx plus h minus fx all over h. This is called the derivative with respect to x of the function f. In some textbooks, you will see a function is written in terms of y. And instead of writing the derivative of f as in f prime x, you can write it as dy dx. In some older textbooks, you will see this notation. And I think this notation was borrowed from Leibniz. How can we interpret the derivative? These are two interpretations here. The derivative of f is the function whose value at x is the slope of the tangent line to y equal fx at x. Now, what does that say? What does that say? It's saying that, okay, if you have a curve and you found the derivative at this point, well, the derivative here is really equal to the gradient of the tangent. See, you see the problem drawing tangents, right? It's the gradient of the tangent at that point. This is a second interpretation. If y equal fx, then f prime, or the derivative of f, is the function whose value at x is the instantaneous rate of change of y with respect to x at the point x. In other words, the gradient here is how y is changing with respect to x at that point. And this is a very useful interpretation, especially when you're going to look at how two quantities change in various areas in science. And we're going to look at many examples later on in the course. But before we go into, using this definition to study rates of change and so on, what we need to do is use the formula that Newton and Leibniz came up with to differentiate some very simple functions, or find the derivative of some functions, some simple functions at that too. And the process we're going to use is what we call differentiation from first principles. And why we call it force principles is because we are making use of the very idea that Newton and Leibniz came up with. And it's summarized in this particular formula that we have here. That the derivative of fx is equals to the limit as h tends to 0 of fx plus h minus fx over h, right? And of course, the condition is that h cannot be 0. And we're going to use this formula to differentiate a couple of very simple functions. Let's take a couple of examples. Let's start with this one. We want to differentiate the function fx equal x cubed. And we are using, of course, the formula that we have. So where we see, of course, the function is x cubed. So where we see x plus h, the function fx plus h, that means x plus h cubed minus fx is x cubed all over h. When we expand that out, and you can always pause the video and work this out and so on, see what you get, right? We get that. Simplifying further, we get this. Dividing through by h, we get this. And then as h tends to 0, this term here, 3xh plus h squared, will be practically 0 as well. And the expression boils down to be 3x squared. And therefore, 3x squared is the gradient function of x cubed. So if you want to find the gradient of x cubed, when x is 1, you just substitute 1 in there. If you want to find the gradient of x cubed at x equal 2, you just substitute x equal 2 in there. So you see how powerful differentiation is? In that it now gives us a function that can give us the gradient. We don't have to draw anything. We don't have to construct any tangent and then find the gradient at different points. No. We now have a function that we can calculate the gradient very easily. Let's take another example. Well, this one was dealt with already. Okay, let's take this one. We want to determine from force principles the gradient function for the curve fx equal 2x squared minus x and calculate its value at x equal 3. In other words, we want to find the gradient of that function when x equal 3. So we're using our formula. We're using our formula here. So we're going to substitute x plus h in the place of x there and there, right? Minus fx, which is that itself, right? And that's what you see here. So of course, you can pause the video again, review your algebra and expand this out. You see, you get that. Remove that bracket, you get that. Remove this bracket, you get that. And you simplify. And you simplify, you get this. Factorize out h out of the numerator, you get that. This h and that h cancels out, and you end up with this. As h tends to 0, 2h is going to be practically 0 as well. And you end up with 4x minus 1. So your gradient function or the derivative or the differential of 2x squared minus x is 4x minus 1. This is your gradient function. But you want the value when x equals 3, so you simply substitute 3 in the place of x, and you get 11. Right, so the gradient of the curve fx equal to x squared minus x at x equal 3 is 11. Let's take another example. And this one is a little harder. Just the algebra is a little hard. So we want to find the gradient function of y equal 1 over x. Right? So here, to get this, you just have to put x plus h in the place of x there. Fx is that, so we put it back there all over h. And this particular author makes use of this technique where you multiply both numerator and denominator by x over x, and here x plus h over x plus h. The whole idea is to simplify this numerator here. Again, if you were to check your algebra, you will see that, well, the denominators will now become the same. So this numerator minus that will give you that up there. Simplifies to give you this. This will cancel with that here, and you end up with this. As h tends to 0 now, this whole expression becomes this here. And therefore, when you differentiate this, you get that. Right? I know the algebra might puzzle you and so, but take your time, go back to your algebra and do it slowly. This is another approach to doing the same problem. Again, you can always pause the video and look at the algebra. Here I found the LCM of x plus h and x. And you add those two fractions in the numerator, you get this here. And then you cancel that with that. You get that -1 there, right? You can always clarify the algebra on your own, and you get that, right? That's just an alternative way of doing the previous problem. And finally, in this one, I try to use the old notation. You're not seeing this notation being used a lot, but I used it, where instead of h, we're using common delta x, right? That's common delta. So we want to find the gradient function of y equal 3x squared when x equal 5. So instead of h in the formula, you're going to see a lot of, you're going to delta x, delta x, delta x, delta x, right? Instead of h. That's the only difference. So again, we simplify using our algebra. We take that, we expand it out, we get this. And when we simplify all of that, we get 6x plus delta x. Right? And as delta x tends to 0, it's all going to be equal to 6x. I think this problem is not complete because they ask you to evaluate it when x equals 5. So when x equals 5, right, dy dx will be equal to 5 by 6 or 6 by 5, you get 30. Right? So the gradient of the function y equal 3x squared when x equal 5 is 30. So in all these examples, we were using the idea of differentiation from first principles. So just to recap, we went through the idea of using a limit to find the gradient function of a curve, and it was remarkable how Newton and Leibniz came up with that. And then we came up with a formula that we were able to now use to differentiate various functions so that we can come up with what we call a derivative or a gradient function that we can now use to calculate, not draw and estimate. No, we can now calculate the gradient of a function very easily.